This is part 10 of the series Logarithmic, Exponential, and Other Transcendental Functions. And in the last video, we ended with a couple of examples of integration of exponential functions. So let's go ahead and begin this video with another few examples. Now this example looks a little different than what we've seen before. So take a second and see if you can figure out what our u substitution is going to be. Now what we have here is 1 over x squared times e to the 1 over x. If you use 1 over x as your u, then the derivative of 1 over x will be 1 over x squared with a minus sign out front. So that would give us the proper value. And hopefully you can see that the pattern we're looking for is e to the u du. This exponent is generally going to be our u substitution. So let's try that. If u is 1 over x, then du becomes negative 1 over x squared. That gives us our proper pattern. We would have e to the u times the derivative of u, which is 1 over x squared with this extra negative sign. We just pull that negative sign out, constant multiple rule, and we have the integral of e to the u du, which of course, as we can see here, is e to the u plus c, and that negative sign just follows us all the way down. And we back substitute for the u, negative e to the 1 over x plus c. Let's go ahead and work another example. Alright, well I can almost feel the tension generated when we display a trigonometric function here, but hopefully this won't be so bad. Let's consider again what we're going to use for our u and our du. Hopefully from the last example you saw that we want a e to u du. So we're going to pick cos x as our u. Our du becomes negative sine x. Again, this negative sign comes out, and the sign replaces the sine x dx here, and we have e to the u du. Again, the integral is e to the u plus c, so the negative sign stays out front, and we do our back substitution. So the integral of this is negative e to the cos x plus c. Let's go on to another example. Now here we have a definite integral. So the process is going to be the same as before with the antiderivative, except now we have to consider the limits of integration here. And so we're actually going to evaluate the antiderivative at these upper and lower limits. So again, consider your u du, and then we'll proceed. Here I picked negative x as my u. My du becomes negative 1 dx. I put the 1 out there just to exemplify the fact that it's a 1. We usually don't write the 1, of course, but it's there nonetheless. The negative sign comes out, and we have the integral of e to the u du. Now notice the limits of integration changed. Now what happened there, because here we're integrating with respect to x, here we're integrating with respect to u. So we have to change these values to be with respect to u. So I take this 0, substitute it in for the x, and we get our u out. So 0, negative 0, of course, is 0. We put in the 1 for x, and the new u becomes negative 1. So this integral becomes negative integral from 0 to 1 of e to the u du. Then we take the antiderivative, which is just e to the u, evaluated from 0 to negative 1, these new limits. We substitute in e to the u at negative 1 is e to the negative 1 minus e to the 0. E to the 0, anything to the 0 power is 1. So this gives us negative 1 over e minus 1. Now, notice I switched this. You don't really have to do that, but just to make it more proper, I guess, I'll just put that way. That would be the exact value. Here would be your approximation. Let's go ahead and look at another example. Here we have another definite integral. So let's consider what our u du substitution is going to be. Now, hopefully you noted that if we took the exponent as we normally did to try and get an e to the u du, that wouldn't work, because if u is x, du is just 1, and that doesn't match this denominator. So it looks like we're going to have to use the denominator as our u, and we're going to have a different integral form here. So if we pick u equals 1 plus e to the x, the denominator, the derivative of that is simply e to the x dx. And that is the numerator, which is an interesting switch. So what we have here is 1 over u du. And hopefully you can recognize that as a natural log form. Again, we have to change the limits of integration because now we're dealing with integration variable of u as opposed to integrating with respect to x. So when we put in a 0 for x, we get 1 plus e to the 0, which is 1 plus 1, which is 2. And then when we put in a 1 for x, we get 1 plus e to the 1, which is just 1 plus e. Now we go ahead and take our integral. The integral of 1 over u du is simply ln of the absolute value of u, evaluated from 2 to 1 plus e. We do our substitutions, the upper limit and the lower limit. This is our exact value, and then we can get an approximation if we need to. Let's go ahead and look at one more example before moving on. Now this one's going to be different than all the other ones we've done in the past. We have an interesting combination here. See if you can figure out what your u is going to be. Now hopefully you chose e to the x, because if u is e to the x, du becomes e to the x dx. And that gives us our pattern. So we would have the integral of cos u du. So that's what I did. I picked u equals e to the x, du is e to the x dx. That matches this, and this becomes cos u du. Again, we do a substitution of our upper and lower limits. So negative 1 into x gives us 1 over e for the lower limit. And a 0 for x gives us a 1. E to the 0 is 1. So the integral of cos u du is just sine u evaluated at our lower and upper limits. When we evaluate it, it's sine of 1 minus sine of 1 over e, which is approximately 0.4818. The next topic we're going to discuss is how we handle exponential functions with bases other than e. But before we do that, I want to do a review of the basic logarithmic properties, because you have to have a pretty good handle on those. So let's go ahead and do that. So here I've given a little list of some of the most common logarithmic properties that we've looked at in the past, and that are going to be pretty valuable to us in the near future. Let's start out with this one. This is the change of base. If you have log to any base of any object, that is equivalent to the log of some other base of that object divided by the log of that same alternate base of the base of this logarithm. And one way to remember it is, notice how the object is above the base, so the object goes on top and the base goes on bottom here. Now this could be done with converting log to the base 10 of some number. This would be the number to the natural log. Let's say that log to the base c, let's say the c was e. Log to the base e is just natural log, and that's the most common choice. So we would have natural log of this object b divided by natural log of this base. Let's say it was 10. If we just did log of b, the base here, this base a, would be 10. You can do this for anything, particularly if you don't have a calculator that will automatically do logs to any bases. Some of the older calculators don't do anything but log to the base 10 or log to the base e, which is ln. So this is a very, very valuable one. We're going to use this to assist us in integration and differentiation as well. The next property is log to the base a of 1. is 0. Log to any base of 1 is 0, and that's simply because the graph of any logarithmic function always has an x-intercept of 1, 0. The next property is the product rule property. Log to the base a of any product of variables is log to the base a of the first term plus log to the base a of the second term. Then we have the exponential rule or power rule. Log to the base a of x to any power is the power out front times log to the base a of that object. And then we have the quotient rule. Log to the base a of x over y is log to the base a of x minus log to the base a of y. And if you remember in previous videos, we proved these properties. Then we have this basic conversion. This shows the inverse nature of exponentials and logarithmic functions. Always remember that logarithms are just exponents. This log expression is just an exponent. Notice this is the exponent. This base a is the base of that power function. So logs are exponents. That's an easy way to remember the relationship between logarithms and exponential functions. Then we have this. This is probably one of the most important conversions you're going to use. Any base, when we have the power of that base raised to a log of the same base as the number here, those cancel each other out. So a times log to the base a of x is just x. That's, of course, assuming that x is greater than 0. And the inverse is also true. Log to the base a of a to the x. Notice the bases are the same. That's just x here. Now, this property is so important that we're going to look at this in greater detail because it forms the foundation for our handling of exponential functions with bases other than e. So let's go ahead and do that. Here we have a more formal definition of exponential functions with bases other than e. If a is some positive real number that's not equal to 1, and x is any real number, then the exponential function to the base a is denoted by a to the x and is defined by this expression, a to the x equals e to the ln of a times x. This is simply a trick of exponents. We're using properties of exponents. If you notice that e to the ln of a is just a, because this is e to the log base e. Notice the bases are the same, as you remember in that last picture that we saw. When the bases are the same, they cancel each other out. So a is the same as e to the ln of a. When we raise that expression to the power x, any expression to a power raised to a power, you multiply the exponents. So these exponents are being multiplied together. So this is a basic identity here. And this is the caveat. If a equals 1, then y equals 1 to the 1. 1 to any power is just 1, so that's a constant function. I have several examples that I want to work, but time is running a little short in this video, so I'm going to reserve that to the beginning of the next video. And so I'll go ahead and end this part here, and I will talk to you in the next video.